Hello, everybody. So thank you to the SOC and the organizers to give me the opportunity to present my work. And so, yes, this work is about AO-PSF modeling. And so I will present an analytical and parametric and parsimonious models we are currently working on at LAM and Onera. So first of all, the context. So you know that we are observing with adaptive optic systems, so through the atmospheric turbulence. And so we have here these scientific instruments that could be science imager, for instance. And so you know that at the focal plane, this image is a convolution between the object and the PSF plus noise. And this object can be, for instance, an extended object, like we see here a synthetic image of Vesta, an asteroid. And you see here the observation with spheres imposed in the visible. And the point is to say that between what we've got here and what we would like to have, the astrophysical quantities, so for instance, here we would like to retrieve the high spatial frequencies, there is a post-processing stage. And this post-processing stage requires at some point knowledge of priors on the PSF through, for instance, a model. So that's why we are currently working in AO-PSF modeling. And so last year, a new model has been proposed by Romain Fétic et al. And so it's a parametric and parsimonious model. So it involves a few parameters. And it's a model of the power spectrum density of the residual phase, first of all. So you see here a cut of the PSD. Here we have the DM cutoff frequency. And this PSD is split into two parts. We have the high order part here. This high order part concerns all the spatial frequencies that are untouched by the deformable mirror. So basically, they follow a Kolmogorov power law. And so this part depends only on the R0. So we have one parameters here. Then for the low order part, we model this using a Morphat function. So this Morphat function depends here on four parameters. We have A, which is basically the energy, so the residual waveform error from the AO correction. We have alpha, basically the PSD will have maximum. P, which is the elongation parameter, so you can account for asymmetric PSD and asymmetric PSF, and beta, the PSD slope. We have also this background value to connect the low order to the high order part. So basically, it mimics somehow the aliasing effect. And so we have here in this model 6 parameters, and two, the R0 and the A, the wavefront error, are main parameters. The others are mostly secondary parameters. So when you get this model of the PSD, you have a straightforward expression of the PSF through this double Fourier transform. And so we have a parametric model of the PSF. And then the game consists in fitting, in calibrating this PSF model using the focal plane image. And so to do so, we use a classical minimizer like a Levenberg-Marquardt minimizer to minimize this criterion. So we have here the extracted image, so point source image. We have the PSF model, flux, and asymmetry plus a background, basically. And so in the end of the day, you end up with a calibration of the PSF plus an estimation of the parameters. And so basically with this framework, you can diagnose the whole system, so the residual waveform error, and also observing conditions like the others. So we have tested this model on several, quite a bunch of PSFs, but actually acquired on 7 different instruments working in the visible or in near infrared. We have sphere Zimpole in the visible, sphere Irdis in the near infrared with high fold ratio, NIRC2, KKO NIRC2 in the near infrared with a segmented telescope, Sol Lucy at LBT with a pyramid wavefront sensor in image in the near infrared, Canary Kamikaze, so working in different modes, SCAO, multi-object adaptive optics, and also ground layer adaptive optics, Galaxy Muse, so at VLT, working in the visible from 450 nanometers to 930 nanometers. And so we have asynchronous PSF measurements at different wavelengths. And GEMS COI, so I've got data from J, H, and K bands. And so it's nice because we have also a PSF in the wide field of view of JCOI, so basically 85 by 85 axons. And so you see here we have on Sky PSF fitted model and the residual, and basically we see at a glance that this model can match quite well any flavor of AOPSF, regardless the imaging wavelength, regardless the complexity also of the system. More quantitatively, we have here the shred ratio retrieved from the model, measured on Sky, also the same thing for the Fourier maximum. And here we have some numbers. So basically the median condition on the shred ratio, the median condition on the Fourier maximum, biases on measurements, and 1 sigma standard deviations, and the Pearson coefficient, the correlation factor. So a summary is given here. Basically, we have almost 95% of correlations. So you see that we have a straight line. This model complies with a high shred ratio values, although there's maybe more discrepancy, and so I will talk about this later. In terms of shred ratio accuracy, it's 3%-ish. And keep in mind that with classical PSF reconstruction work, for instance, we're currently doing at Keck, we end up with the same error on the shred ratio. So with this kind of model, which is again parametric, parsimonious, analytical, we can do as good as a PSF reconstruction pattern. And in terms of Fourier maximum error, it's like 0.2 pixels, basically. Okay, so with this model, we're quite confident in this model in its capability to reproduce an AOPSF, regardless, again, the complexity of the system and the imaging wavelength, the observing conditions, and so on. So then we would like to, before this, another verification, which is, I think, interesting, is here the single estimation of the R0 estimation. And you see here the R0 estimation with respect to the field position we've got on GCOI images. So we have a wide field of view, we extract several PSFs, we do the fitting game, and we end up with a sync value at different field position. And we do not expect this sync value to be field dependent, because this sync is estimated from the PSF wings. So again, the aspatial frequencies that are untouched from the DM correction. And this is what we observed actually. Also, we can do the same exercise on Muse. So this time we have the sync value at different wavelengths. We rescale, so to get this thing at 100 nanometers. And so when you do the rescaling, you do not expect to have any dependency with the wavelength any longer. And this is, again, what we observe. So this is interesting. These results are interesting to show that this sync estimation from the focal plane image is quite meaningful. Then we would like also to improve these results and also to improve the robustness of this of the parameters estimation in the presence of noise and model errors. And so that's why we are currently investigating with colleagues at LAM to develop a convolutional neural network that will be fed basically with the image, the focal plane image, and provide us with the PSD parameters. And so very quickly on this, we've got preliminary results using simulated PSF to train the network. So we have simulated 500,000 PSFs, no noise so far. And we have a classical convolutional network architecture. And you see the versus plot for the 6 PSD parameters. And basically, we have almost no error on the parameters reconstructions. So of course, there's no noise so far. And so the point will be to introduce the noise, the model errors, and we expect to have a better robustness to the parameters retrieval in the presence of worse standard to noise ratio. Last is also to include the static aberrations. And so what we did with this model is to run the model by including static aberrations. So we express the static aberrations in any model basis you want, like Zernike modes, KM modes, or co-phasing or piston modes for the cake, for instance. And you see here on Sky PSF at cake, query in H-band. You see the results of the fitting by fitting only the 6 PSD parameters, the residual. And then we include the NCPA calibration done at the beginning of the diet. So you see that we can improve the residual by a factor by 50%. And also then we include the fitting of 36 additional parameters to account for the presence of co-phasing errors. And so when we do so, we end up with a large improvement on the residual map by a factor 3. And also we end up with calibration, some constraint on the co-phasing map. That compares quite well with previous work done by Sam Ragland et al. 2 years ago. And Sam was only fitting one mode here, so this staircase mode you see here, while in our study we are fitting 36 piston values. We can do the same exercise on sphere here. So this time we would like to retrieve or to constrain the impact of the long wind effect on the PSF. So we model the long wind effect as a combination of the piston tip and tilt modes over the 4 segments of the pupil. You see here the image, here it is in H-band. So we have a strong asymmetry due to the long wind effect. When we try to fit the model by fitting only the 6 PSD parameters, we cannot reproduce very well this asymmetry of the PSFs, and we end up with a quite large residual map. But when we fit 12 additional parameters, so piston tip tilt, we end up with a very good reconstruction of the PSF and an improvement of a factor of 3 on the residual map. And we also end up with a calibration on this static aberrations map that compares quite well with Zelda measurements made during the same night. So the message here is with this kind of framework, we can have good constraint, or we can calibrate basically, or we can diagnose basically the AO performance, the observing conditions, and also have information about the static aberrations coming from the telescope or the long wind effect. Last point is about post-processing, because we can also use this PSF to do this post-processing, which is the original, the main topic. And so with colleagues and mostly with Laura Schreiber, we have simulated observations of R136 with James Leo COI. So you see here a composite image combining G, H, and K bands. You see the shell ratio in the MCAO. So we have these hot spots due to the LGSs. And so basically the point was to measure astrometry and photometry using the standard pipelines, Starfinder. And so we have compared 2 different operating modes. One is the classical mode, so you estimate the PSF empirically from the image directly. Another mode is to provide Starfinder with a grid of PSF coming from a PSF reconstruction or coming from this model. And so here you have a comparison on the color magnitude diagram. And so you see 3 different diagrams, the truth in red. Okay, so this is a simulation, so we know the truth. The classical Starfinder mode in blue, and the upgraded version of Starfinder in orange. And so you see that thanks to the constraint we put with the model, we can get rid of the biases, basically on the photometric measurements, and we can also improve quite a lot the photometric precision by up a factor 10, actually. Also, we can look into astrometry. So same comparison. So this time we have the position error. And again, if we use the original version, We have biases on the PSF because we have special variations of the PSF. You saw the digital ratio map that are maybe not accounting for with the original version of Starfinder, or at least you have to segment the image, and at some point you end up with these biases. But if you constrain the PSF, this time you can get rid of the bias again and improve the asymmetric precision by a factor 4. So next step of this work. So we are currently working on the use of this CNN to improve the estimates parameters, the parameters estimation. Sorry. So basically, so far we are currently working with no noise simulations, but we are going to include the noise, train the network on the noise, include model errors, and go for on-sky tests. Also, we would like to do the other way around. So basically estimate or constrain the PSF from AR telemetry. So using also this kind of machine learning techniques. And we expect to have a PhD thesis, in collaboration between LA, Monera, and ISO, working on this next year. And last point is about PSF determination for IFS. And so this time we would like to benefit the representation of the PSF at different wavelengths to enhance the PSF recovery. And we have a new PhD student, Alexis Lowe, who is currently working on this. Thank you. I'm done, and I'm ready to take questions.
Okay, thank you very much for this very nice talk. So we have many questions. So one question by Scott Will. How much data do you need to be able to accurately retrieve parameters for a given PSF for the classical minimizer, not CNN?
For classical minimizers, so how much data do you need to be able to?
No.
Not sure. Well, just need a single PSF. From a single PSF, you retrieve the set of parameters you want.
And the single PSF has to be recorded using a cube or a certain time.
Yeah. So it will be a long exposure PSF. So basically, you need to have at least a few seconds of exposure to have the convergence of the atmospheric residual. But from a single PSF, long exposure PSF extracted from the field, you can retrieve the parameters. Of course, if you have more PSFs in the field, you can have better constraints on the PSF.
Yeah. So another question here by Miska Leloir. Can you take into account large tip-till residuals in your PSF model?
So we could upgrade the we could definitely upgrade the model. So far we do not distinguish between the tip mods. We do not do this model separation, but that's something I've got in mind indeed to upgrade the model with a specific part dedicated to the tip mods. Yeah.
Okay, so we have other questions. So I will maybe two quick questions. Do you expect that training your CNN on simulated data will be good enough for you? Do you need to train that on Sky PSFs?
I expect it won't be good enough. So that's why we need to have. So either we work a lot on simulations to make sure that the simulations reproduce as much as possible the real observations, but we know it's not. It won't do. So the point is to explore what we call domain adaptation techniques and use a few sets of on-sky PSFs to unbias the neural network. So yes, at some point we need to have on-sky PSFs, but we need to have on-sky PSF regardless with PSF determination techniques. So,
okay, and just a last question, and I recall that you can answer the questions in the Slack directly. Okay, so last question by Tim Morris: does the model work well with images from instruments that don't sample the PSF at the diffraction limit, such as larger spaxel EFUs, things like that?
So for instance, for Muse, we've got undersampling, and so we still have a good recovery of the PSF.
Okay. So I encourage you to complete the answers on the Slack, and thank you very much, Olivier.